Calculus is the study of change. Comes from the Greek word for very small rock. And the idea is the Greek used these small rocks to calculate things, and so hence we get the name. But it means the study of change. So in physics, change is fantastically interesting, so of course it's going to be really great for us to study calculus in order to do our physics. Even though this class doesn't require calculus, and you're probably either in calculus now or you'll take it next year, calculus is incredibly important for our class, so we're going to go through it quite a bit. So there are two branches of calculus, and there is what's called differential calculus and integral calculus. Integral calculus and differential calculus, the two branches of calculus, are united in a really exciting way in the final, the first class that you're taking, calculus, unites them in the fundamental theorem of calculus, which is awesome, and we'll get to that by the end of this series of talks. The idea with differential calculus is you're interested in the slopes of lines. And what we'll use, the thing we'll use to find the slopes of the lines, is called the derivative. And in integral calculus, we're interested in the area under a curve. That doesn't make much sense. What's a curve? What's the area underneath it? You know, it seems like stuff goes down forever, right? But I could draw a little picture that helps you understand that. If I draw an x and y axis here, and we get some function that's doing this or something, we call this thing the curve, and the area underneath it is everything down to the x-axis. That is the area under the curve. Okay, so I didn't like that much. It lends itself some very interesting things like this. If I put negative y down here and x, and this is my function, then this is actually negative area. Because it's below the curve, the function is below the curve. Sorry, the curve is below the axis, so this is negative area. Okay, but let's go back to differential calculus, where we'll be for a couple of these lectures. Differential calculus is interested in finding the slope of a line and taking the derivative to do that. So I'll present to you some function. Let's see, we've got x and y, and maybe it's doing something like this. The problem is the slope varies, right? So what are we going to do? We're going to have to decide where we're talking about the slope of this line, because if I say from here to here, then the slope is there. We could calculate some things like rise and run. And we could divide rise by run and we could get some slope. But if we take these points closer together, like here and here, then we get a different rise and run. And so we'd find a different slope if we zoom in between those 2 points. So in calculus they have to be very careful about it. Math people are very careful about zooming in using a form called a limit. But we don't need to worry about that because we're physicists. The idea is we're going to zoom in. So let's take the derivative a few times. And we've done this in physics already. So I'm just going to call up your memory of how position, velocity, and acceleration are related. Here we go, taking the derivative. Let's start with a function of a pig flying through the air. We know that position as a function of time for this pig, if it was just launched, the pig's going to be launched straight up, then the pig will start out at some position, that's the height of the trebuchet, say, and it will go up, 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 eventually reach a peak, and then fall back down in a wonderfully symmetric parabola, right? So what we want to do is we want to find the velocity of that pig as a function of time. Now, initially the velocity is going to be positive, right? At this instant right here, the pig is shooting upward, and here's velocity as a function of time. At this instant right here, the velocity of the pig is 0, and I guess right here the velocity of the pig is the opposite of what it was when it started. So we're going to give it an initial velocity, let's say right there, upward, then it means positive, and then we can graph this sucker like that. A steadily decreasing velocity until, I guess, pig hits the ground. Maybe, let's say right here the pig hits the ground, and then the velocity is 0 after that. That's the velocity of the pig as a function of time, and this process is called differentiating, or taking the derivative. There it is, we have just differentiated. And the next step will be to look at the next derivative. Perhaps you can predict what that's going to be if this is as a function of time. If I look at the slope of this function, let's talk a little bit more about slope. You know that this graph right here has a slope that's positive right here at the point where this line intersects, and so we graph a positive velocity. Here the slope is smaller but still positive, so we still graph a positive slope, but it's smaller. Here the slope is 0 because it's perfectly flat. Slope is the velocity, and the slope is negative here, so we get a negative graph down there. So the next step is going to be to differentiate again. Let's differentiate again right here. Let's notice the slope of this velocity graph. Slope of the velocity graph is negative at this instant right here, and it seems to be always the same negative. Always a negative slope because the slope of the line doesn't change. So this is tricky. We've got a slope that's steady and negative. This is a pig launched through the air. Anybody want to guess? You want to guess what this is? Is naturally the acceleration, and this value, negative 9.81 meters per second squared. Interesting to think about the units a little bit. Position, measured in meters. Velocity, measured in meters per second. And acceleration, measured in meters per second squared. So every time we differentiate, we're finding that we're dividing by seconds again. Another thing I want to point out is this definition of V average. V average we've defined over the past year as delta x divided by delta t. Now that's not calculus language at all. That's not very fancy. That says if you have a position versus time graph and something's doing this, you say this is the initial position and this is the final position, and you're supposed to find the change in x, which is just the rise, and then you're supposed to divide that by the change in time, which is ti, tf, which is the run. And so of course that's the slope of this position versus time graph. But we can define something now called instantaneous. The instantaneous velocity is defined as dx dt, and the d's mean that the time interval for the slope is negligible. Well, let's say that it's 0. No time. We're zooming in, zooming in, zooming in so much so that we know actually exactly what the velocity is at that time. And people in math fuss a great deal about being very careful about that, and that is not at all our concern today. So let's go through another of these. Derivatives. Let's say we'll start out with. This time the pig is being launched from the ground level, and we'll find that it's actually very similar. Pig being launched from ground level goes up, comes back down, and if we differentiate this, we're going to find velocity as a function of time. And so what we'll do is, we'll say that the velocity starts out positive. The slope here is positive. Let's see. Take slope. Taking the slope is the same thing as differentiating. And so we need to find the slope here. The slope is, well, positive, then 0, and then negative. So we're going to have a very similar shape. And if we continue, we can find the graph of acceleration as a function of time. And that is a negative number because this is a negative slope and it's consistently negative. And again, we get the same shape. So I guess what I want to call your attention to is this is what we had first, and this is what we had later. Notice that the initial x position has nothing to do with the slope. We have exactly the same velocity and exactly the same acceleration, regardless of how high the pig is when the pig is launched. So I want to make this a little bit more functional for you. So I want to use what I call the math language instead of the physics language for just a moment. So I'm going to find a function, and I'm going to ask you to find the slope of that function. And the way we write that is df dx, or we write it as f prime. And we could just put in parentheses to remind ourselves that we're finding the slope of that function. The first function that I'd like to consider is 7. What is the slope of the function 7? You need to picture it, right? The function 7 is 7 because it doesn't depend on x. This is a function that should depend on x if it wants to, but the slope of 7 is 0. So then we can generalize it, and let's say the function c, some constant, 72, 18, who cares, right? Its slope is 0 all the time. What about the function x? This is the function that gets, well, let's check it out. It's the function that goes like that. If this is y and that's x, this function has a slope the whole time, and that slope is, well, the slope is 1. So something with a constant value has a slope of 0. It doesn't slope. Something with a increasing value steadily has a slope of 1. I guess that makes sense. What about if we have 7 times x? That's going to make this line right here steeper. Well, a lot steeper. 7 times steeper, right? This is 7x, and this is just x. Okay, so we've got y is x and y is 7 times x. If it's 7 times steeper, then its slope is going to be 7 times bigger. Pattern, you see it? C times x. Whatever I multiply x by in my function is going to change the slope by c. Okay, reasonable. Check this out though. This is very interesting. This might be the first one that actually surprises you. If I have a function x squared, let me draw a picture of that for you over here. X squared is a beautiful function that makes a parabola. We've got y here and x here, and this is y equals x squared. And it never goes negative. But the interesting thing is the slope is not a constant. All of these slopes have been constants so far. But this slope gets bigger and bigger and bigger as we go forward. So clearly the slope depends, I need you to really consider this. The slope at 0 is 0. And the slope over here, well, it's bigger. And the slope over here, it's bigger. So the slope depends on the value of x. Very, very interesting. What about over here? When x is negative, the slope is very steep, but it's not positive. It's a negative slope for negative x. So let's try this out. It's actually 2 times x, and that 2 is going to be the mystery for you. That's okay. We'll put a big red question mark here because who knows what's going on with that thing right there. But the slope is 2 times x. So let's just reiterate some things we already know. If I put c times x squared, you want to say that it's, well, every time we multiplied by a constant, we simply got that constant out. Let's see, this number here, 0, is 0 times a constant. This 7 here, we just multiplied by 7. This constant right here was the answer for x multiplied by a constant. So let's just take this as 2 times c times x. I guess that's what that is. And save these in your notes. I'm going to get a new page, but you keep what you've got right there. And I'm going to continue this process where we put the function as it depends on x, and then we put the derivative df dx, and some people call it f prime. So let's get another function out here. What if I have x to the third? X to the third, a wonderful little function that comes up like this and goes like that and then goes like that. So this is y and x, and this is y equals x to the third. Let's, you know what, let's trace this sucker out. If I'm going to try to find the derivative of this sucker, then I need to investigate the slope at all times. Notice still that the slope is 0 at 0. So I'll put that right there. Here, this is going to be a graph of y prime and x right here. I'm trying to make my graph. Over here, the slope gets bigger, right? Definitely gets bigger as we go over here. But what about over here? The slope, as we go further to the left, the slope of this function gets, what's it doing? Is it getting bigger or smaller? Look at the slope of this line. Is it getting bigger or smaller as I go further to the left? The slope of that line is getting bigger again. This is, in fact, a symmetric function. You recognize it pretty well. It looks like a parabola. It is actually 3 times x squared. Go figure. Go figure, right? Shall we continue? X to the 4th? You want to guess? Yeah, it's 4 times x to the 3rd. What about x to the 5th? 5 times x to the 4th. And now it's time for you, if I have this as x to the n, it's time for you to tell me what goes right here. Well, it's a power of x, right? But how does the x power change? It is not the same as this one over here. If this is n, it's not exactly n, it's n minus 1. But what is the coefficient each time? The coefficient is the previous power of x, which in this case we're calling n. So we've got ourselves a little formula for how to get this, and then if we multiply it by a constant, x to the n is, well, we're just going to have this multiplied by c. So I'll do c n x to the n minus 1. No problem, right? What if I wanted to add some stuff together? What if I had some of this and some of that? Let's try it out. So I'll draw the sine function so we can see what this sucker is doing and try to find its derivative. If this is y and that is x, the sine of x starts at 0, 0, comes up, goes down, goes up again, and does that forever and ever. This is the sine of x. So we're going to want to try to find the derivative of this function. And the idea is that at each instant we want to know what the slope is. You're going to love this. You're going to absolutely love it. So at this instant right here, the slope is actually the biggest it ever is. I'm going to use orange for my slope. So that's a big slope. And we'll see it again right here. That's our biggest slope. So we can put a dot as high as we can possibly go right here. And again, right here, we'll put another dot at that same height. Good. The slope, usually it's a good idea to find out where the slope is 0 also. I would say the slope is 0 right there, and the slope is 0 right there, and the slope is 0 right there. So let's take some dotted lines down and put a 0 slope there, and a 0 slope there, and a 0 slope here. What about this? We don't have anything. Look, I'm looking at this graph of the slope and I don't see what's happening right in here. How would you compare this slope to these two slopes right here? It looks like there's symmetry around this point right here, and in fact there is. The sine is a very symmetric function, and it's antisymmetric actually. But this graph and that graph, whoa, they have opposite slopes. So we're looking at the most negative the slope ever is right here. And in fact, if you follow this pattern, you see something really beautiful happening. Let's use a blue line to trace these suckers out. If I go like this and connect it like that. Have you ever seen that function before? It's like on your milk cartons, right? The heck is that function's name? Starts when it's at 0. It has a value of 1. It goes down. It comes up. Should we get some numbers on here? Some values? I'll tell you what. This is 0, and this is 360 degrees. This must be 180 degrees, and this is 90 degrees. This sucker right here, probably 270 degrees right there. Okay, let's see if we can make some sense of this. This is at 0 degrees, we're getting a reading of 1. This is bounded between 0 and 1 and negative 1, of course. At 0 degrees, we're getting a value of 1. At 90 degrees, we're getting a value of 0. At 180 degrees, we're getting a value. I don't have a dotted line here. Shame on me. It's terrible. At 180 degrees, we're getting a value of negative 1. And this is the cosine. So, let's put this up on our table. If the function is sine, then its derivative is cosine. We can do a couple more pretty easily now. Just get these down and then we'll be finished for the day, actually. df dx equals f prime. What if we have, what if we have the derivative of the cosine of x? Look at this. If I have the cosine function, and I want to find its slope is 0, and then negative, and then 0, and then 1. it turns out that the derivative of the cosine function is very similar to the sine, but it's not actually the sine. The derivative of the cosine function is the negative sine. What about the derivative of the negative sine? Derivative of the negative sine, well, we know already from this table that the derivative of the sine is a cosine. So the derivative of the negative sine is the derivative of the negative cosine. And since the derivative of the cosine is negative sine, then the derivative of the negative cosine is negative sine of x, which you know better as sine of x. That's it.